Theorem. If A, B, and C some sets, then the following statements hold true. The first statement says the intersection of the sets A and B union C is equal to the union of the sets A intersection B and A intersection C. Similarly, the second statement says the union of sets A and B intersection C is the intersection of A union B and A union C. The complement of A union B in C is exactly equal to the intersection of the complements of A in C and the complement of B in C. Similarly, the complement of A intersection B in C is equal to the complement of A in C union complement of B in C. The identities A and B are called the distributive laws, whereas the identities C and D are called De Morgan's laws, named after the famous British mathematician and logician Augustus De Morgan, who lived in 1806 to 1871, who also introduced the term mathematical induction, which we will discuss in some part of this lecture. If A and B are subsets of X, then De Morgan's laws can also be expressed in this form. Since if C equals X, then the complement of A union B in C is the complement of A union B in X. So the left hand side of this statement is that, and the right hand side can be replaced by this and that. Similarly, the statement D can be written in this form effectively. Let's try to prove statement A. To show these two sets are equal, we need to show that one is the subset of the other. Let X be an element in the set in the left hand side. This means, by definition, X is an element of A, and for this we have an and, X is an element of this set. So X is an element of A, and X is an element of B, or X is an element of C, or this, or. So X is an element of A, and X is an element of B, or X is an element of A, and X is an element of C. So from here, we can write X is an element of A intersection B, or X is an element of A intersection C. If we combine these two by OR, we can write X is an element of A intersection B, A intersection C, and due to the OR, we can write the cup. So this shows that the set A intersection B union C is a subset of the set A intersection B union A intersection C. In a similar fashion, we can also prove that A intersection B union A intersection C is a subset of the set A intersection B union C, just by following the steps we followed earlier backwards. So we just need to follow the steps from here all the way up to here. That will show this statement. These two sets must be equal. The proof is done. Cartesian product of two sets. If A and B are two sets, then the Cartesian product of A and B, denoted by A cross B, is defined as the set of all ordered pairs of this form, where the first element in this pair is in A and the second element in this pair is from B. So A cross B is defined to be the set of all ordered pairs A comma B, where A is from A and B is from B. We note this: the pair A comma B is not same as the pair B comma A unless A and B are equal. For example, this pair is not same as the pair 3 comma 2. That's why it is called an ordered pair. Order matters. For example, if A is a set with elements 1 and 2 and B is a set with elements A, B and C, then the Cartesian product of A and B is defined to be this set. Set of all possible pairs whose first element is coming from A but whose second element is from B.